Yeah. So as you can see, the topic is regarding singular values of random matrices, in particular the largest and smallest singular values, and why they come up and why they are sort of ubiquitous in many applications of mathematics, in data compression, in linear algebra, in numerical linear algebra algorithms, and so on. So it doesn't hurt to have a quick recap. I guess all of you know what singular values are, but there is this very nice geometric interpretation, is that if you consider M cross N matrix, this is one advantage of having singular values. You can talk about non-square matrices, eigenvalues restricted to square matrices. But anyway, we will later on only restrict ourselves to square matrices anyway, so that's not too relevant. So A is a M cross N matrix. Then we consider this map. By the way, just one last confirmation: my screen is visible, I am audible, and my cursor is visible, right?
Yes, all three of them.
Okay, thank you. Okay, so you have a map from Rn to Rm, which is just multiplication by A. And what happens is, if you look at the unit ball in Rn, we will denote it by Sn minus 1, that goes to an ellipsoid. And an ellipsoid is basically a generalization of an ellipse with these directions. And the singular values are precisely the lengths of these semi-axes. This is, say in this case, the largest singular value, and this is maybe the smallest one, but yeah. So the notation will be such that, okay, we'll write them in decreasing order, and many of you know singular values for their useful for the singular value decomposition. This is a very nice canonical form in which we can write a matrix. So you can write, for any matrix A, we can decompose it as a unitary, and then a diagonal matrix, quote unquote diagonal matrix, because this need not be a square, and another unitary in Rn. So basically what is going on in this decomposition is that the map from a sphere to an ellipse is being decomposed into a rotation, and then a scaling along the those semi-axes, and then a rotation of those semi-axes. So this is sort of a geometric way of visualizing what the singular value decomposition really is. And notice that V is a unitary from Rn to Rm, and U is a unitary from Rm to Rm. Okay. Now we won't be needing much of it, but just a recap. And we will henceforth be restricting ourselves to square matrices. Singular values have a very nice feel to them, in the sense that they are very easy to interpret geometrically. When you're working algebraically, eigenvalues come up very naturally as the solutions of the characteristic polynomial. However, singular values, even though they are eigenvalues of other matrices, but the singular values come up very much when you're dealing with certain geometrical problems. And as an example, when you're restricting to square matrices, the singular value decomposition looks like this, where all the singular values are positive. They don't have to be strictly positive, but they're just positive. And we will be especially concerned with the largest and smallest singular values, that is S1 and Sn. Now, of course, by the description of the singular values that I've given, the geometric description, these two equations are obvious. You're taking the largest semi-axis, and the length of the largest semi-axis is the largest singular value, and the length of the smallest singular semi-axis is the smallest singular value. Like this is, say, the large S1 of A, and this should be Sn of A. By the way, one thing, here I'm writing this too, but eventually I'll stop writing it. So whenever I just write a norm, I mean the L2 norm. I'm saying this because I'll also be working with the operator norm of a matrix, and so just to avoid confusion, I think most of you are familiar with the operator norm, what it is. Okay. So this is a sort of a quick description of what the singular value of a matrix means. It sort of describes how much a matrix distorts this particular sphere. If you look at the collection of all singular values, that sort of serves as a footprint of how badly the matrix behaves. If you have an identity matrix, all the singular values are 1, so that's a good behavior, quote unquote. But anyway, let's. But in particular, these singular values, the largest and the smallest, have very nice interpretations. In fact, the largest singular value is exactly the supremum over x in R of norm AX. And for those who know, this is exactly the definition of the operator norm. This is how much an operator can at most can scale a vector by at most. As sorry, there is a mistake here. This should be in Sn. If you take the infimum over R, it's always infinity, and also this should be in Sn minus 1. Okay. And this sort of gives us an idea of the size of a matrix. And okay, and this smallest singular value is a measure of the invertibility of the matrix. Of course, if the matrix is invertible, there is a vector such that Ax is 0, which would mean that the infimum is of course 0. But not just that, even when it's non-zero, it gives a more quantitative measure of how far it is from being invertible. If we look at the set which of n cross n matrices M and R, and I'm basically describing this, and we look at this set S. S is the set of all singular matrices. Then any matrix, let's say you have taken non-invertible an invertible matrix, the smallest singular value of A is precisely the distance between this set and this matrix. So it is the infimum in the operator norm of A minus S, such that determinant of S is 0. So that is S is in the script S, the set of all singular matrices. So that gives a very nice intuition of what these represent and why they are sort of useful. Studying the size of a matrix and the invertibility of a matrix are the two most fundamental questions in linear algebra, and the same in other places because linear algebra is ubiquitous. So these are sort of natural statistics that we would like to study. And another very natural statistic is the so-called condition number. Notice one thing, that the singular values depend on the scale of the matrix. So if you double the matrix, you double the singular values. However, if you are looking at the largest singular value by the smallest singular value, that's the size upon the invertibility, that is scale invariant, and also this captures the amount of distortion that this matrix A is causing to your Rn. The moment you take a map from Rn to Rn by multiplication of this matrix, this is how large a vector can become, and this is how small a unit vector can become. So this sort of measures the distortion, which is evident from our previous diagram. And these three quantities, the largest singular value, the smallest singular value, and the condition number, arise in many places. One example is numerical linear algebra. So I'll put an example here. These are not, I won't be getting into these much in the talk, but just for motivation. So when you are dealing with numerical linear algebra algorithms, we have heard that when, say, we are doing Gauss-Jordan elimination or calculating the inverse, something like that, the problem becomes harder as the matrices become get closer and closer to being non-invertible. So for singular matrices, of course, you cannot find a inverse, but even if it's close enough, it becomes very hard to, it becomes a very long procedure. So as it turns out, the time complexity of such algorithms is governed by this condition. Okay. Then the question arises, what typically is the value of the condition number of a matrix? So when you have an algorithm, you want to know, let's say you want, one question you can ask is, what is the worst case time complexity, worst case space complexity? But another question is, what is the typical space complexity? On an average, what do you get? And such typical values are very important in analyzing what algorithms are good and what are bad. So the question arises, what are typical largest singular values and smallest singular values if you just take any matrix? As it turns out, von Neumann and others in the 1950s, they ran very extensive computer simulations, and they sort of came up with these hypotheses or conjectures which are given here, that the largest singular value is about the order of square root of n, but not much larger than that. The smallest singular value is of the order of 1 over square root of n, but not much smaller. So most matrices are non-invertible, so we would have expected a greater than 0 value here, and we do get a strictly greater than 0 value here. And and then you can just divide and say, okay, the condition number is at most some factor times n. It's at most linear in n. And then he wrote this and said typical. Now, what does typically mean? How do you quantify this notion that, okay, typically if I take a matrix, this is what I would observe? How to make this precise? That is where probability comes in. That is why we need random matrices. And this is like, this is not why we need random matrices. Random matrices come up in various places, but in this particular problem, this is where randomness enters. Okay, so we start with, by the way, if there are any questions at any point, please feel free to stop me. Then don't wait till the end of the talk or sometime else. Just ask me then, unmute yourself and ask me then, or write in the chat, and the people in the technical team would tell me. Okay. All right. So there we are. That is where random matrices enter our story. We want to basically prove these three results for a class of random matrices and say that, okay, for this class of random matrices, these three results hold with high probability, with exponentially large probability. These three results are true. That is the result that we intend to prove at the end of today's talk. Okay, at least sketch, if not completely prove. So random matrices. A random matrix is basically just a collection of random variables. We are always dealing with square matrices in this talk. Is a collection of random variables where the i's are all random variables, not necessarily independent, nothing. They can be any random variables, whatever. So there are many sort of models of random matrices which one can ask for. You can say, okay, what if all aij's are some distribution? What if they have this kind of dependence, that kind of dependence? But for our purposes, we'll be looking at the IID model of random matrices, which, I mean, to me at least, is the simplest. Is that all the aij's are IID some distribution xi, and we will put restrictions on the xi as well, because we want to make some quantitative estimates. Something like Cauchy would be horrible to work with. So for this talk, we'll consider xi to be centered sub-Gaussian random variables. When I say centered, I simply mean that the expectation of xi is 0. Sub-Gaussian, in some way, I want it to be dominated by a Gaussian random variable. In what way? That's it. That's what I described here. So the first definition of the talk, mathematicians can't live without definitions and theorems and proofs. So the first definition, a random variable, you look at a random variable on some property space, is said to be centered sub-Gaussian. Centered is a separate thing. It just means the expectation is 0. If with a parameter sigma square, if the moment generating function exists, that is the expectation of e to the power tx, that is moments, exponential moments exist for all t, and that it is bounded by this function, exponential of sigma square t squared over 2. And those of you who may have worked with moment generating functions may know that this is exactly the moment generating function of the Gaussian random variable. So if z sigma follows normal 0 sigma squared, the moment generating function is exactly this. So in this sense, we mean sub-Gaussian, that the moment generating function is dominated by the moment generating function of the Gaussian. Okay, and okay, so one can say that, well, such random variables are very hard to come by. Maybe Gaussian is, after all, a very special random variable. So what are examples? Well, firstly, Gaussian, of course. A Gaussian automatically satisfies, it's an equality. Normal 0, 1 is sub-Gaussian with sigma square, the parameter sigma square equal to 1. Another wonderful example is all bounded random variables. Whenever you have a bounded random variable, you can show that it satisfies this equation for some sigma large enough. In particular, we would be looking at this Bernoulli plus minus half random variable instead of the normal Bernoulli half random variable which takes values 0 and 1. this takes values minus 1 and plus 1. Okay, so that because we want centered, so that the expectation is 0, and so throughout the talk I'll be talking about Gaussian or sub-Gaussian random variables, but I always want you to keep these two examples in mind. That is the standard Gaussian, the normal 0, 1 random variable, and the discrete case, that is the Bernoulli plus minus half, also called the Rademacher half random variable. Okay, these will be our prototypical examples. So of course, if y is follows normal 0, 1, then y is sub-Gaussian with parameter 1. This will be our notation, sub-Gaussian with parameter 1. And if y follows Bernoulli half, as it turns out, it's also sub-Gaussian with parameter 1. It's a basic calculation. You can look at the moment generating function. This is the explicit moment generating function, and then you expand it in Taylor series and see that it's less than or equal to e to the t square over 2. Okay. And for general bounded random variables, you can do actually a similar thing to show that it is bounded by e to the power sigma squared. Some sigma squared will come here for some large enough sigma, but it doesn't concern us right now. So henceforth, we will just take not just sub-Gaussian, but sub-Gaussian with parameter 1, because as discussed in the very beginning, whatever we are doing depends on the like the smallest and the largest singular values are like we know what happens to them when the matrix is scaled. So we can maybe just normalize the matrix and make our life simpler and look at sub-Gaussian 1 instead of sub-Gaussian sigma squared. Okay, and this is the key thing to keep in mind. That is, the moment generating function of such a random variable xi is always less than or equal to e to the t square over 2. I hope there are no questions at this point. And why such a thing is useful? Because we will use Kramer bounds, or rather I should say Chernow bounds. So we will have to look at exponential moments, because we want, at the end of the day, remember, no, I haven't talked about it. Sorry, you can't remember, but okay, I'll talk about it soon enough. We will use Chernow bounds eventually. That is the reason. Okay. So this is our matrix model. Our random variables, matrix looks like this: Aij. Aij's are all IID. This random variable xi. A bit atypical to use a small letter as a random variable. We generally prefer capital letters, but bear with me. Where expectation of all the Aij's is 0, and that the xi that we are dealing with is sub-Gaussian 1 random variable. So we will now give a resolution of von Neumann's conjecture and describe what we mean by typical and atypical values. And okay, so let us just call this is our matrix model, right? So let's call this OMM. So if A follows our matrix model OMM, then these are the theorems that we'll be getting at. So the first theorem is involving the largest singular value, and it says that the largest singular value being larger than a constant times square root n can be given an exponential bound. In particular, for k however large, for small k, for whatever value of small k, there exists a capital K such that this bound holds. In other words, this is the case. This is sort of the notation we will use. A is less than in probability of order of k square root n root n. So this tilde just means that up to some constant, and this p means with high probability. Okay. So with exponentially large probability, this is the sense in which von Neumann maybe meant atypical, in the sense that with exponentially large probability you have such a bound. Similarly, we have a bound for the lowest singular value, for the smallest singular value, which is here. So there exists, not C1, sorry. So let's say A is from our matrix model. Then there exists constants capital C and small c, such that for all epsilon positive, this is not exactly an exponential bound. It's a combination of a linear bound and an exponential bound, but the message is the same, that with high probability its sigma 1 of A is larger than or equal to 1 over square root n. So the smallest singular value is of the order of 1 over square root n, and the largest singular value is of the order of square root n. And as a corollary of both of these theorems, we would immediately get bounds on what we wanted on the, this is the condition. Okay, this is the sorry, I'm sorry, yeah, this is Sn. Yeah, this should be Sn. Sorry, thanks. So we would get bounds on the condition number, and that would help us with our linear algebra algorithms that we have not talked about and that we will not talk about. But yeah, we will talk about these bounds. Okay, let's start with the first one, the operator. Now there is this obvious geometric interpretation of, I have dropped the 2, see, no 2, but it's a supremum over this set Sn minus 1, and it's easy to see that instead of taking supremum over the non, I can take this double supremum over the inner product. It's a very standard tool that we use, and then what we wish to basically bound is say that sigma 1 is not larger than epsilon root n with high probability. That is, we wish to give an upper bound to this probability. This is exactly S1. All right, but if I say this a supremum is greater than epsilon root n, that just basically means there exists x and y in Sn minus 1 which are greater than epsilon root n. So it basically this is like a union of events. It is a union of events of the form axy. I should not maybe use exy, where exy is the event that this happens, and whenever we see that, the first thing we think about union bound. But there is a problem with the union bound at the moment. Can anybody point it out what the problem is? This is the event.
This union is an uncountable one.
Exactly. So there is, we have, even if we can give wonderful bounds to this guy, there is no hope of giving a good bound to the probability. So we'll have to come back and tackle that problem. But till then, let's look at one of them. Let's just look at one of them. So what about fixed x and y in Sn minus 1? Okay. So now we see why we took such strong bounds on the moment generating function, because if you look at the moment generating function of this random variable ax comma y, is a product, we have the expectation of we can split it up. But now notice that all of these terms in the sum are independent, so we can take this sum out as a product because it is sum in the exponential. So by independence of aij's, so by the way, x and y are fixed vectors. Yeah? Aij is the only random thing, and this product again, aij is sub-Gaussian, so we have e to the s aij is less than equal to e to the s square over 2, which just gives us this, and then we can pull the product back in, and we have this. So sums, Gaussian, sub-Gaussian random variables, and independence. These three are like a golden pair. They work very well together. But anyway, that gives us that this random variable that we are talking about, axy, is also sub-Gaussian with parameter 1, and it is of course centered. So now we have everything to go for a Charnock bound. So the Charnock bound simply looks like this. As usual, we raise it e to the t times something like this. For some t positive, we will later optimize it, and then we use the bound to get this. And I think I take t to be epsilon root n here. Yeah, that will optimize the result to give us this. So that's a wonderful result. That probability of such a random variable being greater than epsilon root n is e to the minus epsilon square n. We have got an exponential bound on each of these probabilities. We wanted a exponential bound on the union, so that's a good start. But now we have to work with how to talk about the union. So for that, we somehow need to discretize this here. Before discretizing, let's ask, why should we even want to discretize? Why should we not give up here and say, okay, this union bound doesn't work? Because a union bound is useful. let's say you have two probabilities. Okay, I'll just erase this. Let's say you have two events, A1 and A2. When is such a bound close to being tight? Such a bound is close to being tight when A1 and A2 are almost independent events. That is when such a bound is useful. If they are dependent, it's a useless bound. And that is why we realize in the union bound argument that we are putting up here, we are being rather wasteful. Look at the sphere, okay? Look at the sphere and look at this map, which takes x to the modulus of axy. This is a very well behaved map in the sense that it is continuous. It's Lipschitz continuous. In fact, it's very well behaved map. So once I can control it for one point, I have basically controlled this quantity in a neighborhood. So instead of looking at individual points, what I should be looking at is individual patches, and then take a union over these patches. Hopefully the number of patches will be finite, and we will get a finite union. And if I have chosen the patches correctly, then I would get a so these two patches, if they are pretty far away, they would be sort of independent, and then the union bound makes sense. All right, so that is what we now try to do. So the questions that arise are, where do I write? There is no place to write. Okay, so I'll write here. The questions, we wanted to patch things up, right? Patches. So the firstly, we need to give a nice description. Give a description of these patches. Secondly, we would have to make sure that they are sort of far apart and independent and so on and so forth. And the main idea is that ensure that controlling this quantity norm x y on one point of a patch would control it over the entire patch. So ensure control. That's all. These are the two things that we want. So let's first give a description of the patches. Let's discretize the sphere. We define an epsilon net of the sphere to be a collection of points such that any other point, if I put in any other point, there is some point in the collection such that the distance is less than epsilon. That is what I mean by an epsilon net. And there are many ways of constructing an epsilon net. One obvious way is to just, if you take the cube in Rn and you fill it up by epsilon balls, all right, and then look at those epsilon balls which intersect with the sphere, and take those as your patches, and any point from those epsilon balls to your patches. And what about the cardinality? The number of epsilon balls should be 1 over epsilon to the power n, something like that. And as it turns out, you can find an epsilon net which has a cardinality which is less than 3 over epsilon to the power n, and that order and the dimension both make sense, because that's about like something like c over epsilon to the power n is the number of total balls in a cube. So the number of balls intersecting the sphere should also be something like that. And as it turns out, this is a tight bound. You can't do better than this. And these are results from geometric function analysis, which we are sort of using here. Although this is a very easy result, but the ideas we are using throughout the proof of discretizing and using epsilon nets and so on, these are techniques borrowed from function analysis and more geometric sides of function analysis. Okay, so but then there is the second question. We have got epsilon nets, that's great. How do they help us control this? The answer is yes. Look at let's start with the operator norm. The operator norm on this is of course defined like this, but look at the point from M. So there exists a point xz such that z minus, okay, we start here. Let's say we are taking M and N to be half nets, okay, of Sn minus 1. So of course their cardinalities are like this. They're less than 6 to the power n from our previous lemma. Now, if you're looking at the supremum, we can split it up and use triangle inequality. And because there exists such an xz in M such that this holds, such that the distance is indeed less than half. And then when we take this out of the supremum, this is less than half. So this is bounded by half of the operator norm. And the second quantity, we are taking a supremum over z of axz, but that's exactly just taking a supremum over M of this epsilon. And once we have gotten this, we can take this to the other side, and we see that bounding the operator norm is exactly the same as bounding the bounding sort of a discrete version of the operator norm. So there we were taking a supremum over all points. Here we are just taking a supremum over points in M, and that does not give us much of an error. In fact, it gives us a bound up to this factor of 2. So that's great, and we can repeat the argument again to this norm of Ax, and that would give us a bound in the exact similar vein. This, we again look at this W. This is exactly a supremum because, well, one side is clear, less than is clear from Cauchy's inequality, and the greater than would be you can just take W to be Ax by norm Ax. Anyway, and this you can again split up and then use triangle inequality and use that this is the norm, the modulus of this, or rather the norm we should say, is less than a half to get this result, and again we get this. So basically, instead of working with this guy, so this is equal to the supremum of norm Ax y, where x and y are both in Sn minus 1. So instead of working this sort of continuous union, supremum over a infinite set, we could do as well with the supremum over a finite set, just up to some factor. That factor won't matter because anyway we are not dealing with the linear factors precisely. So the rest of the proof is smooth sailing. The probability that each of them is that the operator norm is greater than p root n is this exactly. But now we expand it out in the union bound, and these the cardinalities of M and N come out. These we will often be calling the entropy factors, because this will sort of denote the number of terms in this expression. And okay, I'll just be calling them entropy factors. Let's not go into a discussion of why. And this term here is S36 to the power n, and we get this. And the second term is exponential. So taking t appropriately, I can of course define. I can of course show that for any k positive, I can take this this exponential to be small enough, and so for any small k, there exists a capital K such that this result holds. You can the non so we can just have to take t large enough. What do we have to take? So this is just exponential of minus n square over 4 plus log 36, whatever. So if we take large enough, we take t large enough, we get this result, and then replace t by k, just expression. So that is the proof of the first one, and let's just quickly reflect upon what we did. What we did was we did a very sort of, this is a very standard method of proof in these kinds of things, is first we give a bound for a fixed vector, for a fixed or a fixed, not a vector here, for a fixed x and y, for a fixed pair of vectors we give a bound, and then we extend it using union bound, but not on the entire set, on patches. And to work with those patches, we look at epsilon nets, and and epsilon nets, as long as you are dealing with a sufficiently good function. In this case, we are dealing with this a x comma y. As long as you are dealing with a sufficiently good function, which is continuous, and I think you need Lipschitz. As long as you are dealing with a Lipschitz function, all of this exact same argument would work. This is a very powerful technique to give bounds to supremum of functions on metric spaces. Okay. And this is often called a covering argument, and that eventually leads us to this result. So that is an intermission. There ends the first proof. Any questions, doubts, comments, insults? Huh? Sorry.
Hello.
Yeah, go on.
Yeah. Can you just scroll up a little bit?
Yeah.
Yeah. So in that m and n, those entropy factors.
Mm-hmm.
I mean, okay. Can you somehow optimize that constant? Like, will there be some?
So you want this 36 to be gone and something smaller in that? Actually, no.
Okay.
The thing is, I did not give an argument for why this is exactly true. And what I'm saying is these epsilon nets. This is actually true. I mean, you cannot get epsilon nets which are much smaller, because if you're dealing with an n-dimensional object, you need n many things, and I gave a sort of vague argument that okay, to fill Rn you need 1 over epsilon to the n many things, and that's why you get here. But you can actually give a much more precise argument and say that this holds. I think. Let's see. N epsilon is equal to 1 plus 2 over epsilon to the n minus 1. Like sorry, the n, and I think this is 2 over epsilon. I might be wrong, but this is basically what you get. You cannot get a much smaller epsilon net. And this is actually another way of defining dimension, combinatorial dimension. I think VC dimension is defined in similar ways. Is that if you are dealing with a combinatorial object, which is maybe embedded in Rn, maybe embedded in some metric space, an alternate way to define dimension is to look at what like how big epsilon nets do you need to cover that. So a sphere in this regard is also n-dimensional as a combinatorial object, not in the metric space, not just because it is because it's sitting in an n-dimensional space. And there are of course things which are like say trees, which are infinite dimensional, or lattices which are finite dimensional, and you can sort of get a different idea of dimension in that way. But this bound is more or less tight. There is no way to improve it, and that is a problem actually, because in the argument that we'll get to in the next part of this, the working with a singular value, I would have paid good money to get better epsilon net bounds, but we don't have that. That's why we have to work much more carefully, and the argument becomes a lot more convoluted. Okay. So, any other questions? If not, I'll just drink some water and then we move on. All right. So that was all about the largest singular value. The largest singular value comes up in many computations. It is a very useful thing to know is how bad your how like big your matrix scales things, and we have somehow managed to obtain a good bound on this. So by the way, another comment is that we use sub-Gaussianity, but not very strongly, in the sense that you won't get an exponential bound unless you use sub-Gaussian, but you can get some bound. Yeah, that's all. And now we come to the second part of today's talk, which is how to bound the smallest singular value. Okay, so before we try to bound this smallest singular value, let's look at this formula itself. What is it trying to tell us? We have a linear bound, and we have a linear term and an exponential term. What exactly do they mean? And this is where we'll get to those two prototypical examples that I wanted you to keep in mind. Is that, let's say you have Aij is IID normal 0 1. Then you can actually give a more direct argument. Normal Gaussian matrices are the best behaved matrices, and Gaussian independent matrices are even better behaved. So then one can give a direct argument show that this is when I say tilde, it's less than or equal to some c, and also greater than or equal to sorry, I'll just some small c epsilon. Okay, so this is this quantity, the singular value being smaller than epsilon over root n, goes exactly like epsilon. And that is sort of the source. That is why we need this linear term in there, not like the previous time. We cannot just throw in an exponential term and be happy with it. And the other side of the coin is, why on earth do we need this exponential term? Because if you're dealing with discrete random matrices, if and I put epsilon equal to 0, that has a positive probability. So RHS cannot be 0. In particular, if I take Bernoulli plus minus half random matrices, then if you look at the singularity probability, let's have a look at it. The probability of singularity is at least the probability that two rows or two columns in A are equal, right? So or they are plus minus one of each other, and if you compute that, you can show that this probability is okay. Let's do it. Let's say you have this is your matrix A, and the probability that any two columns are equal is 1 over 2 to the power n, but you can choose the columns in n choose two ways. Similarly, it is singular if the rows have such a relation. So you multiply by 2. And similarly, the rows and columns could be minuses. So if you have two rows which are minus, whose sum is 0, then again you get a singularity, and so on and so forth. But whatever you get, you get something of the order. So you basically get a polynomial times 1 over 2 to the power n. So you get an exponential term, an exponentially decaying term, and that, so you have to have the singularity probability is of course always greater than an exponential term, and that is why we need this term in here too. So this formula is telling us about two distinct behaviors going on for sub-Gaussian random variables. One is that their extrema is very well controlled, so we get this linear term, and also there is some, since we are allowing discrete random variables, there is some singularity probability. So that is what this formula is capturing, and it is somewhat surprising that that's enough. There's no other weird behavior out there. You don't get a quadratic term. That's enough. Okay. So, and also one more idea is that this, of course, I've talked to you already about this, is that this gives a quantitative approach to the invertibility of this matrix A. But what about, why don't we try working using the determinant? Why don't we just look at the invertibility all by itself? The reason is determinant is a nasty polynomial. When you're dealing with matrices where all entries are IID, the determinant takes them and intertwines them in such a horrible manner that you cannot extract independence out of it. And as you may have noticed in all our arguments, we are using independence very crucially. So this sort of idea is maybe triable, but does not yield, cannot, or rather should I say, does not work well with geometrical approaches. Because your determinant has very nice algebraic properties, you can maybe try algebraic approaches, but throughout this talk we'll be only giving various geometric approaches of tackling such problems. So, well, with geometric approaches. Okay. All right. So now let's actually dive into the problem. Now, how would we want to bound the singular value, the smallest singular value? It won't be as easy as in the previous case. And what we'll have to do is we'll have to basically split the sphere, the Sn minus 1, into three parts. The first one are sparse matrices. Okay, let's just, yeah. So sparse matrices are those which have control support. The support is small. It's delta n. Okay, so we are fixing a delta, and the support is small. So if we look at a three-dimensional sphere, that's all I can draw. these will be sort of the sparse matrices, the matrices at the corners. If this is the coordinate system, the matrices at all four corners and here and here. These will be sort of the sparse matrices. Here it's a finite set, but if I take delta small enough, but okay, it might be an infinite set in general. And the compressible matrices are am I saying matrices? Sparse vectors, sparse vectors and compressible vectors. But compressible vectors are those which are close to these sparse vectors. Okay, so there exists a row ball such that all of these are closed. All right, and all the remaining vectors, we will be referring to them as incompressible vectors. All of the remaining real estate of the sphere, that is the incompressible vectors. As you can see, most of the volume of the sphere is taken up by incompressible vectors, but we will be dealing with them separately. First, we would like to give a bound on this. We want to basically give a bound on the minimum of norm AX. First, we give a bound over sparse matrices, and then, of course, as you can clearly see, compressible vectors. Sorry, again, compressible vectors are close to sparse vectors, so we can extend that using an epsilon net argument as we did before. And finally, the proof for incompressible vectors will be a much more complicated, a lot more involved issue. We'll get to that soon enough. Okay, any questions regarding the approach? No idea. Okay, so let's go to the first part, dealing with sparse vectors. And again, these sort of geometric ideas are very have surfaced recently. By the way, this is something I should have said before, is that bounds on the smallest singular values are very, very recent results. These bounds are obtained by Mark Rudelson and Roman Vershinin in 2008. Whereas if you go back to the previous one, the bounds on the largest singular value, that is known since antiquity, that people in 1970s knew how to work with it. So these are sort of cutting edge problems. That, and of course, since you're doing something cutting edge, it will be a lot more involved. But this is our approach, that we split the sphere into these two parts, compressible and incompressible, and then we work with that. Of course, sparse vectors are automatically compressible vectors. Okay. So to start with, there is fix a set sigma. Okay, sigma is a subset of 1 to n, where the size of sigma is exactly this delta n, or the ceiling of delta n, and we define R sigma to be exactly those vectors which the support is in sigma. That is, the support of x is in sigma. Everywhere else it's a 0. These are lower dimensional subspaces of Rn. Okay. So now, using the methods that we used in the previous part, one can show this result for sort of such sparse vectors, in the sense that if you are only taking an infimum over this set R sigma basically looks like this. So if you have a sphere, this thing R sigma intersection Sn minus 1 looks like maybe an equator, maybe it depends on the dimension, but such an infimum. So we are basically bounding over an equator of Sn minus 1. And as it turns out, you can use exactly the same arguments that we used before, and in the interests of time, I won't be giving those arguments again, to give a proof of this result. That is, the infimum over such an equator, not the entire sphere, but the equator, is less than or equal to k root n. This probability is well controlled. It's controlled by an exponential term, e to the minus ckn. And when I say ck, it's some other constant k. And of course, as k goes to 0, this event becomes more and more unlikely. Ck goes to infinity. Okay, so we get a stronger and stronger bound as this event gets more and more unlikely. The proof is exactly as in part 1. I would like to leave that as sort of a grand exercise. But anyway, with the remark is that this size of this sigma being small was extremely necessary. We could not have done it for the whole space, and this is where the remark that I made before comes in, is that sadly there are no better bounds on the entropy factor. Had we gotten good enough bounds, life would be much simpler. We wouldn't have to work with compressible and incompressible vectors separately. Okay, but anyway, once we have this bound on our sigma on this equator, on one of the equators, we can sort of extend it to all equators, in the sense that once we have it for this guy, we can do it for this guy. In this case, we only have 2 equators, but you can sort of, in higher dimensions, you can look at all the sparse vectors. Okay, so yeah, there we are. That's where we are. So how many such subsets are there? There are exactly this many subsets, and well, you can use Stirling approximation to give a bound. Then the probability that the infimum of norm AX is less than or equal to k root n. We are now going to abound over all of the sparse vectors, but the sparse vectors that we are discussing here are exactly the unions of those equators, or unions of those lower dimensional subsets of size delta n of Rn, or yeah, and that we can again bound by a union bound argument to get this term. This is the, sorry, I should have maybe written it better. This is the entropy term, the term coming in front, and this is the probability term. Okay, so and that is again, if you take k to be sufficiently small, you get an exponential bound. So we get an exponential bound for sparse vectors. Maybe should I clarify some things here, or is it fine? Sorry about it. It's a bit clustered, I think. But anyway, once you have a bound for sparse vectors, it is easy to extend them to compressible vectors using the exact same technique that we described before. In particular, if you want the infimum over compressible vectors, you can again split this vector x as x minus yx and yx, where yx is a sparse vector, and then that splits up as this infimum, and the second term, this guy is always less than or equal to rho, so you get this term. And also remember, we have bounded this guy previously. We have shown that with very high probability, with exponentially large probability, this guy is less than some k root n. So if I take rho to be small enough, I can take this guy, this entire term, to be less than this entire term, and in which case I would get this result. Okay, and so we are basically looking at this guy being less than k square root n, and this guy. So okay, I should clarify a little. We need rho to be smaller than k root n. Sorry, we need k by capital K. That is what we need. There is no dependence on n, by the way. That is important. So this is the row which works. Okay, but anyway, the notion is clear. There we got, in the previous case we got a factor of 2. Here again we have got a factor of 2 by taking rho to be sufficiently small. So here, instead of that half net, there is a rho k sort of a term here. That's why we want it to be smaller than k over capital K. All right. So this gives us a bound over compressible vectors. So whenever, and actually note one thing, we are after bounds like this. X in whatever x, infimum over x, norm x is less than some epsilon divided by square root n. This is the correct order of lowest singular value. Here this is a much stronger bound. This is a lot stronger than we required. We are saying that it cannot be smaller than root n itself. So for the purpose of attaining the lowest singular value, these compressible vectors are extremely useless. Never in a million years will the lowest singular value be attained at any of these compressible or sparse vectors. Okay, that is what I'm saying. So the lowest singular value will be attained only for incompressible vectors, and that is the major chunk of the sphere. So all of this argument was sort of getting rid of those like few people on the playground to let the big boys in. And now we go to the bigger part. This is where the second, this is probably the main contribution of Rudolphson and Verschinen. That is how to work, how to deal with such incompressible vectors and give bounds to those. Okay. So the thing is, whenever you're looking at a vector which is not compressible, okay, what does that mean? That means it's not close to any sparse vector. In particular, what you can say is, if you have this, okay, so if you look at, let's say this is an incompressible vector x, then mod xk cannot be small for too many values of k. In that case, it would be close to some particular sparse vector. In other words, it's larger than some constant over square root n for at least C2n coordinates. Now, why this square root n? Let's say x is in Sn minus 1. What is the typical value for xk? We want the sum of squares to be 1. So, typical value of xk is about 1 over square root n. Now, in this case, since we are dealing with incompressible vectors, not many of them can be much smaller than 1 over square root n, because if that were the case, then it would be close to some sparse vector, and we would end up getting a compressible vector rather than an incompressible vector. In particular, we can find, and this is the actual sort of precise result, there are constants C1 and C2 such that for all x is in incompressible, xk is greater than C1 over root n for at least C2n coordinates. For at least a linear number of coordinates, xk is large in the sense it's of the order of 1 over square root n. Okay. So now we get to our approach. What we are actually going to do is fix a j, capital J, weird notation, but stick with it. Fix one capital J in this set from 1 to n, and look at this Vj such that Vj is perpendicular to all other AIs except AJ itself. Okay, and then the norm of AX is of course greater than the norm of AX comma B, because if you take the infimum over V, then only then you get an equality. And this guy, it's perpendicular to everything except Vj, so we get this. So this is the J. AJ will denote the jth column of A, and this is the exact equality that we get. Notice, however, that we are dealing with incompressible vectors. So with large probability, this guy is actually bigger than C1 over square root n, with at least linear probability. Oh, where does probability come in? Well, instead of just taking a j, what we can do is we can randomize. We can say pick j uniformly at random from the set 1 to n. Okay, and then the probability, using this, we can say the probability that xj for any fixed vector x, the probability that xj is bigger than this C1 root n is at least C2, because we know that for at least C2n many of these j's, this happens. Okay, so but then what happens is the probability that norm AX is small and that xj is large, this is bounded by the probability that this guy is small. If you look at this expression, this we have bounded below by C1 over square root n, and this we have bounded above. So this gets upper bound basically, and we get this expression. However, this is something that we get almost for free, in the sense by loss of a factor. And also, okay, sorry, ignore that. what I'm saying is that this bound, look at this bound, there is no x, there is no x, and it does not depend on x at all, and the entire process also is completely independent of x, of getting from here to here. As long as it's greater than c1 epsilon over root n, we are happy, and j is a completely independent random variable from our entire setup, which means this we get a uniform bound, that is the infimum over all x incompressibles being less than c1 over root n, and the fact that xj is larger than c1 over root n, that is well bounded, it's well controlled by this. We don't know, oh by the way, so we don't know whether it's well controlled, we know it's bounded by this guy, and again j is completely independent of a and v, so I can just replace j by 1. Was this part clear, or should I repeat? Maybe make some more clarification.
Could you please repeat?
Yeah, sorry. So yeah, basically what we are trying to do is we are trying to give a lower bound to this quantity, sorry, an upper bound to this quantity, and we are saying that such an upper bound is unlikely. We want to give a lower bound, we give an upper bound and say that is unlikely. So we want to give an upper. Sorry, go on.
One question, we showed the inequality holds for all x, so but we are taking infimum inside the probability.
Yeah,
shouldn't that be outside, because we know the probability is less than the upper bound for.
You are quite right, but as it turns out, the procedure is okay. I'll repeat this, and I'm pretty sure it will be clear. So what we are basically doing is, let's just erase all of this thing. There is no confusion about this part, right? This is just a purely linear algebraic result. We can expand it out. Let's call this. Now what we are looking for is basically we have randomized j. Even if we randomize j, this is this holds for all j, right? So even though j is a random variable, there is no difference at all. Now what we are looking for is we are directly, let's we'll be directly looking at the second expression. Okay.
The inequality holds for all x, so we are taking infimum in that inequality itself. So
exactly, we are not taking infimum in the probability. That's why I'm starting from here.
Understood.
Now. Yeah. That is something I should have clarified properly. Is that when we are taking an infimum over this thing, and we are saying that okay, whatever this j is, we are putting in this condition for now. Just we will get rid of this later on, but we are putting in this condition now and saying that xj is greater than c1 over square root. If that happens, then automatically we have this idea, right? So yeah, basically these two events, as was pointed out, this is a subset of this event due to the inequality 1. Is that clear?
Clear.
Yeah. Now we take probabilities, and okay, maybe should not have erased, but let's be quick. Now if we take the probabilities like this, but in the right hand side we clearly see that there is no dependence on j. J and a are completely independent, and vj, this entire setup is independent of j. So we can just say put j equal to 1 or put j equal to any fixed number we want, because j is a sort of an alien random variable. It has no dependence on a at all, right? And by the way, one thing I should have mentioned probably is we want v to be unit. Otherwise, this inequality does not work. So this inequality would fit if we take v large. So we have to take a unit normal of which is normal to AJIs. But anyway, now how to get rid of this term? This term is again you can clearly see this term depends on J, and this term this term basically depends on J, and this term is completely independent of J, so they split up. Alright, and so since the probability of this guy is the probability of this happening for a fixed x is small, it's not small, it's bigger than equal to C2, the probability of this happening, we can take the C2 to the other side and we have a bound. Okay, so sorry about that confusion, but I think we agree that this works, right? So essentially, let's forget all that confusion and what went on and what, but basically what we have reduced ourselves to is taking an infimum over the incompressible vectors and bounding that is exactly the same as bounding this weighted sum. Alright, and also note that VI's are, by the way, one thing I should have said it, VI's are random variables because they are perpendicular, they are normals to a collection of random variables. So this V1, I haven't defined VI's. V1 is a random variable. However, the randomness in V1 and the randomness in A1 are independent because V1 is derived in terms of A2, A3, A4 all the way up to AN, and we can choose V1 in a way such that it does not depend on A1 at all, right? So these two terms are essentially independent. In particular, if I am looking at this term, let's erase this, I can sort of expand, I can do a conditional probability thing, and I can expand it out in this manner. C2, I can look at this, we can condition over the probability that we can condition V to be a fixed vector, yeah, over the randomness in V, or maybe let's just write it V1 itself. And the term inside is precisely a linear combination of vectors, linear combination, weighted linear combination, I should say, weighted linear combination of vectors. So let's say A1 is something like x1 through this.
So what is the event in that probability?
Where?
Expectation less than epsilon, right? Okay.
Oh, sorry, yeah, less than epsilon. Extremely sorry. It is less than epsilon given that given B1 basically. Okay, yeah. So let's say A1 is x1 through xn, and let's, instead of B1, write W1 through Wn. Right. So then this inner product, we are basically left to bound this quantity, the probability that modulus that basically summation xi wi is less than epsilon. Now this classically is a much more known thing to people, is that how to bound linear sums, but we have done it for say wi equal to 1 or wi sparse in general. That is, those are the cases which are known classically, but in general it's a lot harder to work with, but we will work with them now. So all of this work was to say it suffices to bound such a quantity, because the moment we get a bound here, that goes inside and the same bound comes out, right, because it is independent of V1, so expectation over V1 is just the same constant. So that takes us to something called small ball probabilities. All right, let's say, and yeah, so let's say S is a random variable, any random variable, it doesn't matter, and wait, I have never used S, sorry. Wait, just a second. Okay, yeah. So I wrote a definition double, but anyway, so let's say S is a random variable, and we define for, so the moment S is a random variable, it takes values in R. So what we define is the probability of, we look at this quantity S minus V, forget V, S minus A being less than epsilon, and we look at the supremum over it. This is exactly the probability that this S concentrates in, oh sorry, I've used U, fine, let me use U. Concentrates in an epsilon neighborhood of it. That is exactly what the probability is. And we are taking a supremum over U. This is called the small ball probability. Okay, and we'll denote it by P epsilon. Now we get to a setup which is more akin to what we saw before, is that pick W in pick any weighted, this is W is will be used as weights. Pick any random vector, sorry, any vector, not a random vector. Pick any vector from Sn minus 1 and excise as random variables. Then we define this as the small ball probability also as the supremum, and we look at the concentration of this linear sums. Basically, we are replacing S by these weighted sums, and we want to see how well that concentrates and what happens to that. By the way, these are examples of something that we call anti-concentration inequalities. We are measuring, so basically we are trying to give an upper bound to this. Okay, so that would say that being in this set is quite unlikely. If we can give a how unlikely it is, that will give a upper bound to it. So these are examples of anti-concentration inequalities, and yeah. So let's look at again two of our prototypical examples. Let's look at normal, but we want to basically see what this small ball probability looks like. Does it concentrate about some value? If it does concentrate about some value, the small ball probability would be large, because the probability of this being less than epsilon for some U is large. If it's very spread, if the random variable, if this weighted sum is very spread, we would get a good upper bound to this guy. But can we estimate it? That's the question. So let's take the first example, which is normal 0 1, IID normal 0 1. Then the summation of WIXI is also normal 0 1. That's where the rotational invariance of normal comes in. It's a very special distribution, and in particular, you can just easily check that this being a normal 0 1 random variable, that P epsilon of W is of the order of omega, of the order of epsilon, independent of W, completely irrespective of what the W is, as long as it is a unit vector, it is the same thing, the small ball probability. However, that is an exception and not the norm. In general, it depends heavily on what W is. So for if you take xi to be IID Bernoulli plus minus 1, plus minus half, then, and you take W to be 1 over root n, I should take maybe 1 over root n to make it a unit vector, 1 over root n. The probability of this guy being 0 is of the order of 1 over square root pi n, which comes from our standard random walk idea. But if you just take W to be 1, which is also the same thing, which is also the vector with the same norm, then this summation being 0 is with probability half. So there's a huge discrepancy, and it really does matter what the W is. The question is how to decipher what W gives a good concentration and what W does not. So basically, we saw this guy. This is well concentrated. This doesn't. This is not well concentrated. That it does not concentrate too much about 0. But this guy is very well concentrated. It just takes two values, 0 and 1. That's it. Nothing else. The question is how to decipher, given any linear sum, whether that guy is concentrated about its mean or any other value, or whether that guy is not concentrated and sort of spread out. That will be our purpose of the next part of the talk. And why is the not next part, a little bit only, and why is that sort of useful? Because we want to give bounds to this, and this guy is harder to work with, but is basically bounded above by the supremum of Q in R of this probability, right? And by the way, we want this bound is sort of expected to be good because the mean is indeed 0, and this we expect it to be maximized at the mean, of course, or at least close to the mean. So this is the bound we'll use. Yeah. Okay. So this working with these linear sort of combinations of these weighted random variables is the topic. It's called Littlewood-Offord theory, or it is the Littlewood-Offord problem. And this was classically like answered by Littlewood-Offord, and then a lot of other people came and made many a lot of contributions to it, significant contributions. And but we were at the question how to distinguish these two behaviors given a random vector. As you can see in the Bernoulli case, it heavily depends on whether the matrices have a nice arithmetic structure between them or not. In the sense that, in what sense do we mean a good arithmetic structure? Is that we define this LCD. Okay, we define the essential lowest common denominator of a random of a vector as follows. It basically is the infimum over the lambda. Let me draw a diagram. This is a lot more useful. So if you look at such a graph, or rather a grid, and say this is the origin, and this is the vector that we are considering. The essential LCD is the least thing. We have to scale the vector y so that it comes close enough to a lattice point. When we say, let's say we have these numbers 1 over 3, 2 over 5, and 1 over 7. We say the LCD, the lowest common denominator, is 3 times 5 times 7, because that is the number we have to scale by, so that if we scale by the LCD, this actually belongs to this ZL. But in our case, that is not possible. All of these belong to the ZL. In our case, that is not possible unless the vectors have a rational ratio between them. So we are content with having them close to these lattice points. All right. So that is why we call it the essential LCD. And what we are saying is the smallest lambda, such that scaling by lambda, all of the at least kappa many of the indices come close to Z. Not all, we can't guarantee that all of them will come to Z, but at least kappa many indices will come to Z. And we fix some alpha positive and some kappa, which is of the order of kappa has to be of course between 0 and n, but kappa we fix linear. Okay. And once we have done that, this essential LCD is the deciding factor. This will decide whether we see a behavior like this or a behavior like this in case of general sub-Gaussian random variables. And then we get to this theorem on SVP. This is a rather recent result, although the seeds were sown by Halas back in 1979. Is that we say xi, let's say xi is IID a sub-Gaussian one random variable, then the small ball probability is controlled by a linear term plus this LCD. Okay, and plus there is some exponential error term. And for that you have to choose alpha and kappa properly, but I'm ignoring that entire part. And this proof uses Fourier analytic techniques. It works with you have to work with the characteristic function. It's not hard, but there is no point talking about it here. But this is the critical thing that we want to use. Now let's go back to our previous case. What did we wish to bound? We wish to bound something like this, correct? And V1, what was V1? V1 was a random normal. So V1 was perpendicular to this A2, A3, and on and on all the way to the end. But if you have a vector attained randomly, of course its arithmetic structure, it is very intuitive to see that its arithmetic structure, it does not have an arithmetic structure between its coefficients. If it's taken as a perpendicular vector to such like these are IID random vectors, by the way, they have absolutely no dependence on each other. So if I look at the perpendicular vector, it's quite intuitive to expect that it won't have any arithmetic structure, which means this term would be large, which means we would get a sorry this denominator, the LCD, would be large, which means we would get a good bound on our small ball probabilities, and we would get a good bound on this guy. Correct? So that is what was properly formalized by Rudelson and Wigner, is that if you have this random normal. One more thing I should. That's fine. So the random normal V1, this has a large LCD. In particular, the probability there exists constants C and C prime, such that the LCD being smaller than this exponential term is very unknown. In particular, if we condition by this the complement of this unlikely event, that is the likely event, that is the LCD is large, we get the bound that we wanted to boost. Okay, so is this part clear? Just yeah. So because the moment we get a bound on this, we get a strong bound on the we basically get a bound here. That's it. We get a bound here, and that's what it is, because LCD is large. It has probability. So, and combining all the results is that the probability that the infimum over Sn minus 1 is small, of this norm X is small. We can split it by union bound into two parts. The first part we have bounded previously by because we are dealing with compressible vectors, and the second part we dealt with right now, and we got a linear term and an exponential term. This was the source of the linear term. This theorem on small ball properties really was the source of linear term, and yeah. So that gives us the proof for here, and so I have some concluding remarks to make. I'm almost out of time, but let's see. Are there any questions here? Okay. If not, we'll go to some simple extensions. So that first of all, let's go back and reflect upon the argument we made, and at least in the second part of the argument, we never used sub-Gaussian. We never really used the full power of the sub-Gaussian assumption. And so actually you don't need the sub-Gaussian assumption in the case that if you are dealing with random variables which are mean 0, variance 1, and have fourth moment finite, even then the second part is true. But the only difference is you have to put this extra condition in here, because this was sort of automatic from the sub-Gaussian condition, so we never had to put it because it will only give an exponential error. However, in this case, the first part wouldn't work. That is, the bounds on the smallest singular value, those actually used the sub-Gaussian assumption. So we have to put this condition in separately. This is the analog of part. Another thing is why stick to square matrices? There was no reason to. You can actually extend all of these results to rectangular matrices, and if you do extend, the smallest singular value remains the same. The largest singular value actually behaves in a much more the largest singular value remains the same, and the smallest singular value looks like this. The order is now square root capital N minus root over small n minus 1, where A is a capital N cross small n matrix. We demand capital N greater than small n, because otherwise the matrices are not invertible anyway, left invertible, that is. And if we take the square case, capital N equal to small n, we see that capital N minus root over n minus 1, or small n and capital N are both same. So let's just replace both by small n. Small n minus 1 is approximately 1 over root n. So we exactly get the bound that we got in our case. And also finally, this let me talk a little bit more about the singularity probability problem. Is that let's now fix to Bernoulli matrices. And a long-standing problem, I mean very long actually, from the 1940s people have been trying to solve this, is estimating the singularity probability. What we have done is, this is our estimate, this is not from 1940s. We have shown that it's less than c to the power n for some c, and if you trace out the argument carefully, you will see that c is smaller than 1. So at least we have some bound. And also, as discussed before, the probability that two columns or two rows of A are equal, or they are like plus minus negative of each other, that is about half plus some small term to the power n. Now the conjecture for a long time has remained to be the probability that determinant of A is 0 is actually this. So the main reason why such a matrix is invertible, a Bernoulli plus minus random matrix is invertible, is because two of the vectors are sort of equal, or they're minus of each other. And this has a very rich history. Is that in 1967 Kolmos gave the first non-trivial bound. We want this, but we got an order 1 over root n. Then in a remarkable paper, Khan, Kolmos, Gemeridi gave this bound. Tau and Wu in 2007 improved upon that. Then Borgen, Wu and Wood, it's a very recent paper, they improved upon it. And finally in 2018, this conjecture is no longer a conjecture, it became a theorem, and the proof was done by Tikhomirov. So the point is, these kinds of ideas, and all of them used to some extent geometric techniques similar to what we use. In fact, a lot of the work on essential LCD that we use is, a lot of it can be attributed to this paper of Tau and. But the idea is, this is a very happening field at the moment, and there are many such problems which are currently open and in the process of being worked out. Because very recently we have started borrowing techniques from this geometric function analysis and using them to probability. So there's a lot of potential for these techniques to be used. That will be all from my side. If there are any questions, now is a good time. Hopefully I'm audible. Okay. Yeah. So that's good. And here are the references. The references are mainly papers. This is the first paper on. This is actually whatever I spoke about was there in this paper. So this is the paper of Rudolphin and Verschin, which deals with the singular, which the largest and the smallest singular values of square random matrices. The second paper, they published a second paper in the same year, in a few months of time, deals with the rectangular matrix. This was the bound, this one. And there's a wonderful lecture series at ICTS, which was conducted in 2022. It's called Topics in High Dimensional Probability. All of it is recorded in YouTube, and you can look at lectures 1 and 2 by Mark Rudolphin. They cover basically, he covers a lot more material than this talk and explains it a lot better. So, is it 2023? Oh yes, January 2023. Thank you. Yes, last year. So if there are any questions, please let me know, or else let me complete this slide. Wow. If not, maybe I'll stop the sharing. And okay, sure. Yeah, I'll share the notes. Thank you. Hello. Good night.